Alright, let's continue with next part, and this is a part where we are going to derive the mathematical equation which is core in lubrication theory. That equation is named Reynolds equation after the one who derived it for the first time, Osborne Reynolds, in the 1890s. It's a partial differential equation, and when we derive this we start with some assumptions. Some of these assumptions can be removed later, and these are some simplifications for this equation. The most important can not removed. It's a thin film approximation, and that assumption tells us that the lubricant film thickness is much smaller than the length of the bearing. This is normally called a thin film approximation, and which holds very well for almost all bearings and other lubricated contacts. The next one is that the fluid is assumed to be incompressible. We assume that stationary conditions are present, and that means that there is no change in time. We also assume that it's an infinitely wide bearing. That means it's a 1D problem. So it's everything. The motion of the fluid or the lubricant in the contact is only along the bearing. We assume that the viscosity is constant. That means it's isoviscous, and it's no temperature increase, so which also may change the viscosity. We assume that it's a Newtonian fluid. We assume laminar flow. We assume that fluid inertia and body forces are very small and can be neglected. And we also assume that there is no pressure change across the film thickness. That is part of the thin film approximation. Some of these, as I said, can be removed later on. The first step is then to take one small element in this is the bearing again, and this we study a small, infinitely small element inside the lubricant film, and then we apply the forces on that element. So we have the pressure here, and on the other side of the element the pressure also acts, but the pressure may have changed slightly over that small distance delta x. And on this side of the element we have shear stresses. So we have the shear stress tau here, and that tau may have changed a little bit when we move in the z direction, like that. So if we applied the force equilibrium, assuming then zero inertia and also stationary conditions, the equation looks like this. And if you simplify this means that actually this can be simplified to this tau dz is equal to dp dx. And that is, if you study this carefully, you may see that this is the Navier-Stokes equations for the lubrication problem. It's one of the Navier-Stokes equations. And another way to derive this is to start from the Navier-Stokes equation and make an order of magnitude analysis and just drop all the terms that are much smaller than those ones, and you will come to the same result. So these three equations are actually the full set of Navier-Stokes equation in the 3D, because you can do the same for the y direction, and as we already assumed that dp dz is zero since the pressure is constant across the film. Next thing is to think about what kind of fluid we have here, and as we already assumed, we assume that it's a Newtonian fluid. That means that there is a linear relationship between shear stress and shear rate, like this, and the proportionality constant eta, that's the dynamic viscosity, and the shear rate is or the shear rate gradient is maybe a more better name of it, is the how this flow profile changes across the film, because the flow profile or the speed of the fluid, that speed changes with the thickness of the film. And so the UD set is actually the gradient of this curve. So if we now assume that, we take the equilibrium, the load equilibrium equation we already derived, dp dx is the same as the tau dz, and we know that tau is according to Newton's law. Put it into the tau here, that becomes this one, and since eta is constant, it's an isoviscous case, we can take it out from the parentheses, and suddenly you have this expression, and you can reorganize that expression a little bit, and you end up with this one. So the second derivative of the fluid velocity is equals to 1 over eta multiplied by the pressure gradient. So, and you can make use of that expression to find the velocity profile. So starting with this, and then we integrate once, you get that term, and you get a constant, and you integrate again, and suddenly you have an expression for the flow profile. From this picture you also see that if we assume that the lubricant sticks to that surface, and it also sticks to that surface, we also get two boundary conditions. That is that the flow must be equals to u naught down here and uh up here, and you have two constants and two boundary conditions. That's perfect. That means that we can find the values of C1 and C2, the two constants. And making use of that boundary condition, I don't show the mathematics here, you end up with an expression that looks like this. And so here you have one term, and this term is what we discussed before, is the pressure driven or Poiseuille flow term, and this term is the cont'd flow term. So you see them down here. So this is if the pressure gradient is positive, this means that the flow is in this direction. You can see that this speed will always be negative, and for a positive gradient. And the cont'd term is then the flow moving in this direction. It's a linear profile. It's a constant gradient, and it is u naught down here and uh up here. Okay. Next step in the derivation of Reynolds equation is to assume or discuss continuity. That's apart from the force equilibrium, continuity is the second law we must obey always. And if it's an infinitely wide bearing, there is no flow into the screen here. It's just along the x direction. And since there is also stationary conditions, steady state, it means that there is no time effects. That also means that the flow into the gap here must be the same as in this intersection, and as in the outlet. Which means that the flow is constant everywhere. It's the same flow everywhere. And you can express that mathematically as dq dx is 0. And that is actually the continuity equation for this case. Okay, now we have the continuity equation, but that is for the flow. And the flow can easily be found if we know the velocity profile. So the velocity is u, x, z, and we just integrate it over the z direction across the film, and we get the flow. So we just enter the relationship for velocity here, do some integration between 0 and h, and you end up with a nice expression like this. You use that expression in the continuity equation. Dq dx is 0. That means that this equation must be 0, and this is actually Reynolds equation. this is the continuity equation in the form of Reynolds equation. So Reynolds equation is actually their continuity equation. You can rearrange it a little bit and you end up with a format which is normally used in textbooks. And again, this is the Poiseuille term. This is the rate of change of the Poiseuille term must be the same as the rate of change of the Couette term. So this term is driven by the pressure, and this term is driven by the surfaces. So, as I said from the beginning, some assumptions can be removed. For example, compressible fluid is not a problem. Non-stationary conditions is not a problem. A 2D case with a finite width of the bearing is not a problem. Isothermal conditions, not a problem, but makes it more complex. That's the same also for the non-Newtonian case. Turbulence can be treated also, fluid inertia as well, but these are very much special cases. This case cannot really be treated by the Reynolds equation and shouldn't. Then you really need to use the Navier-Stokes equations if you really require that, but that's pretty seldom you do. First step, compressible lubricants. Instead of using the volumetric flow as we used before, you just use the mass flow, and you follow the same route when you derive the equation, and the equation look very much the same. The only difference is that you enter density here now. Density here and density there. This is the change of mass flow, and this is the Poiseuille mass flow, and this is the change of Couette mass flow. So very easy. The non-stationary contacts are necessary to study pretty often. Can be journal bearings with a dynamically loaded in an engine, for example. Another engine example is the lubrication of the piston rings and the cylinder liner. And that means, and the third example is rough surfaces. If you have two rough surfaces and one of them is moving, the whole film gap, the distance between the film or the thickness of the film will continuously change. It will vary rapidly with time. So if you have this variation of film thickness with time, the continuity equation looks a little bit different. So you follow the same route when you derive the equation, but when you derive the continuity equation, it's a little bit different. If you take a small element again, control volume in the film, you can study the flows in. That's the mass flow is rho density multiplied by the volumetric flow, and you can study the flow out, and that is the volumetric flow plus the change over the small distance delta x. But then there is also another change of this control volume, and that is if it expands or if it becomes smaller, and that is controlled by the h rho h the rho h dt term. that tells you if this term is positive, it means that the mass in the element is growing with time. If it's a negative, it becomes smaller. So you actually do the mass flow balance here, and you end up with an equation like this by studying this small element. So this is the new continuity equation for the non-stationary case. You see the difference here is that you end up with a term d rho h dt, and you follow the same pattern here. Then you use the equation for the mass flow, and that must be the same as the change of the mass of this element. So if you rearrange it again as it normally is written in textbooks, it looks like this. Again, Poiseuille term, Couette term, plus the time term, or this what is normally called the squeeze term. So this is the non-stationary Reynolds equation. Then you can do the same thing also for the y direction, the direction into the screen. What is happening is that you end up with another term, another pressure-driven term. It's in the y direction, and you get a wet flow term in that direction too, and you get the squeeze term. This is the full Reynolds equation in 2D. Normally you use a coordinate system that all the motion, the surface motion, is in the x direction. That means that this term is normally dropped, but there are some cases where you need both. So a short example of how you can use this Reynolds equation to solve the equation and to learn from that solution what about the conditions in a bearing. We use a very simple bearing geometry, a step bearing. That means that the fin thickness is constant here, then there is a step, and then it's constant again. So this is a bearing because there is a converging gap. It's a bigger inlet than the outlet here. You apply the Reynolds equation. Since the fin thickness, you take it you solve it piecewise. You solve it first for this part, and you solve it then for the second part. Since the hdx is 0, it's no gradient at all. This means that the right hand side of the equation is 0. You integrate then the left hand side, that becomes a constant, and you integrate again and you rearrange, and you realize that the pressure in the first zone is a linear equation. It's and it will be the same also for the other part. In order to determine the 4 constants, you need 4 boundary conditions, and a proper boundary condition here is that the pressure is 0. Another is that the pressure is 0 here too, and right here at the step the pressure must be the same if you move just a few micrometers to the left or a few micrometers to the right. That means that both P1 and P2 must be the same at this position, and let's call that pressure P max, because you will see that later it is actually the maximum pressure. So by using these those 4 boundary conditions, you will end up with these 2 equations describing the pressure in the first part and in the second part. So you see here in the first part the pressure will vary from 0 up to the maximum P max here, and then in the second part it will be the same. Start with P max and go down to 0. And what about P max then? The P max can be obtained from the continuity requirements, because again the flow in this part must be the same as the flow in this part. Making use of the relationship for volumetric flow, for the first part must be the same as the volumetric flow in the second part. And by rearranging this, you can find the solution for the P max. So you see here that the maximum pressure is higher. The higher the speed is, the higher the viscosity is, the longer the bearing is. And you can also see that the bigger the difference between the 2 steps, the height here and the height here, the bigger the pressure is also. So if you want to learn more about this, I recommend you to read Reynolds' paper. Actually, I was wrong. It was derived 1886. And there is also a book by Bernie Hamrock from 94, and you may also read Anton van Beek's book from 2006 about advanced engineering design, which is very much into tribology and lubrication. So good luck. See you later.